to be honest, Algebra 1. But the calculus test in here, the calculus part, is here. Notice, though, that it takes all these prerequisite skills. And in pre-cal is Algebra 1 and Algebra 2. So the dagger with these, I swear, what costs most kids their accessibility to points on an assessment and an optimization, or what's coming later, our related rates problems, is the Algebra 1, Algebra 2, and pre-cal. Because the calculus, you got. You all know how to do the freaking first derivative test. It's just that you can't get here without Algebra 1 and Algebra 2, and in these applications, even geometry. And so kids will leave it blank, and they're out of a whole bunch of points because of Algebra 1, Algebra 2, and geometry. So just know that it is your prerequisite skills and not your geometry that are rusty, and that's what's holding you up to optimization, which is in reality true about physics as well. Physics is just a bunch of math application problems, and it's not your most recent math. It's not your complicated math that holds you up, or your sophisticated math. It's the Algebra 1 and Algebra 2 and pre-cal and geometry that holds you up. All right, I'm off my soapbox. So here we go. Here's a very classic problem. You'll see this you'll even see these in Algebra 1 and Algebra 2 books, and they just take the calculus out of it and give you a calculator. So we have 40 feet of fence to enclose a rectangular garden along the side of the fence. What is the maximum? So that's one of my first goals. And my maximum, this is the first and second derivative test that find maximum and minimums of functions. So maximum, I say to myself where the first derivative changes from positive to negative, and its area that I want to maximize. So I already say to myself, area is length times width of a rectangle. So I already wrote down here where the first derivative, I'm looking for where the first derivative is 0 or does not exist and changes from positive to negative. So I draw myself a little picture, right? Here's the side of my barn, here's my rectangle, and notice that I made two sides. I chose to make X, could make them Y, could make them Z, could make them T, could make them whatever you want, but I can make them W for width, but I'm a math teacher, so I chose to make W equal to X. But if W, I know some geometry, right? What is the perimeter of 3 sides, right? Right? If I take to enclose this perimeter, I need X plus this side, but if I've already used, so if I have 40 feet of fence, let's suppose that this was, X was 5. So your 40 minus, I used 5 feet of fence here, and I used the same 5 feet over there. Well, isn't that 2 times X? So that's how I get 40 minus 2X, right? When, just plug in numbers and figure out what happens, right? And then I've got 40 minus 10 or 30 left for this side. But isn't 30 40 minus 2 times 5, right? So notice what I've done here, though, is I've made the width and the length in terms of the same variable X. So now I can write an area formula with only X's in it, right? Width times length. So I multiply that out, and shocker, I get a parabola with a leading coefficient that is negative, so it's an upside down parabola. This is a parabola, so the derivative always exists. I know that there is a maximum of a parabola that opens upside down, and I know that a parabola that opens upside down starts off rising, so the first derivative is going to be positive and then change to negative. But I have to show some math here, right? So I take this is a math test, so I take the first derivative, 40 minus 4x, that's a linear function with a negative leading coefficient, meaning it's a linear function. right, that decreases. So the first derivative is positive before its x-intercept and then is negative, corresponding to where there's a max and the original function changes from increasing to decreasing. I set the derivative equal to 0. Make sure you show this part. It's a derivative test. Find the first, or a calculus test, find the first derivative, set the first derivative equal to 0. Solve for the x. Put the x value on your number line. Hey, where did 0 and 20 come from? Can you figure that out? Well, certainly the left endpoint is going to be 0. There are no endpoints to this parabola, right? There are no endpoints here. But in the real world application, if x is the width, certainly 0 would be my left endpoint because I can't have a negative width. And I'm not actually going to use 0, but for purposes of my calculus test, I will make that a closed circle. And then do you see how I got 10? Right? Because if I got 10 here and 10 here, haven't I used 20? Right? And if it's any more than 10, would I have any left to make a width? Right? So suppose this was 12 and this was 12. Isn't that 24? Right? And then what is 40 minus 2 times 24? Right? So just reasoning through stuff like that. Don't spend too much time on a test worrying about the value of those endpoints. Okay? If that's what's throwing you, move on and get to the calculus. So of course note that yes, I have my positive, that the first derivative is positive, my original function is increasing, and my original function is area, so area is increasing to a max, and then area begins to decrease to a min. So therefore, I have a maximum. If you're increasing from a left endpoint, you must be a minimum. If you're decreasing to a right endpoint, you must also be a minimum. I'm looking for the maximum, so my only candidate is 10, and I've proven that it is a maximum by the first derivative test. So if you get through all of this calculus here, and you dutifully write your first derivative, you dutifully set your first derivative equal to 0, you dutifully find your x, and you this and therefore a max, you're going to lose a point here. I know you know it, but I know it's obvious, but it's a calculus test. Please show that you have tested values and that you know that 10 is not a minimum, but a maximum using calculus, right? So you have to show some kind of work here. So probably in general, there's going to be a point for coming up with the function, the area function, a point for taking the first derivative, and probably that same point for setting equal to 0, but maybe not. Maybe that's a whole additional point depending upon how tough it was. Then a point for solving, a point for the work to show that the candidate you found was indeed a maximum. And then, now notice I'm already up to 1, 2, 3, 4, maybe 5 points. But I haven't answered the question. 10 is what? 10 is a width, and notice I have units on it. And the length is 40 minus 2 times 10, or 20. Has that answered the question, though? They asked what the maximum area is. They didn't ask me the width and the length. So I have to go back to my original function and plug in. And notice that it's not just the answer, it's the answer with appropriate units. Okay, so again, that was example 1. And example 1 was a classic problem, and the numbers were all nice, so this could be on a non-calculator portion. So So here are my steps for solving an optimization problem. Firstly, you got to read the words. It is a word problem, right? So in the word problem, you have to figure out the math words and the math directions. What math? Since these are optimization problems, you're looking for the words maximize or minimize. What is it that you're trying to maximize or minimize? Tell me what it is in words. So in the last one it was area. I was trying to maximize area. Maybe another problem, it's minimizing cost, and those two words are wrapped up in a whole bunch of different words. Circle minimize, circle cost, underline maximize, underline area, or something. Then you need to write an equation. Whoops. You need to write an equation. So instead of it being number 3 in the book and the equation says find the extrema on this equation, you have to write the equation, and that's the hard part for a lot of kids. You need to write the equation for the variable that you named and only one unknown. So notice in the previous example I had area equals length times width. That's 3 unknowns, area, length, and width. I had to rewrite the area function A in terms of one variable. So that's how I used x. Sometimes this gets nasty. The algebra part. I know I say pre-cal here, but it's really algebra. Then finally, you get to calculus. And since it is a calculus test, even if like in that previous example it was obviously a parabola that opened down, you need to use the first derivative test or the second derivative test. For extrema, we are maximizing and minimizing things. So your job is to find the places where the derivative is 0 or undefined. Don't forget the undefined. We didn't have to worry about that because we were dealing with a polynomial. Then you need to test them. Test values using a number line or the concavity test. And don't forget endpoints. So there is a handout that has all the examples that I'm going to do over the next couple of days. It is on math groups. If you want to pause and go to math groups and download the optimization examples, you will see that example 1 is the one I just completed. Now I'm going to go on to example 2. Kids struggle with these problems as well, and I just think it's because I am talking about geometry on an axis. So a rectangle has its base on the x-axis and its upper 2 vertices on a parabola that opens down and has a y-intercept and its maximum at 0, 12. Notice all that algebra that I just said in 12 minus x squared. What is the largest area the rectangle can have and what are its dimensions? So firstly, I have a rectangle. I have a rectangle. I have a parabola that opens down. They're asking me to maximize area of that rectangle. And further, they're asking me for its dimensions, length and width. So the first thing I'm going to do is draw a picture using my Algebra 1 skills of my parabola. Then I'm going to draw a possible rectangle. So the base is on the x-axis and the upper 2 vertices are on the parabola. So there's my base and here's the 2 vertices. Now say to yourself, why would they tell me that the vertices are on the parabola? Notice this is the origin. So if this distance is x, some x, say like, I don't know, 2. So let's suppose that x is 2. What is y? Isn't y 12 minus 2 squared? Right? X, whatever x I choose, x of 1, comma, plug that x into 12 minus x squared to get the y. Hello, height. This, then, distance, because this is the origin, 0, if this distance is x and this is a rectangle, right, this distance is that same x just negatized. True? And guess what this height is? Since it's a parabola, which is symmetric across the butterfly line, isn't this point the negative of that x and then 12 minus that same height, right? So I'm trying to maximize area. Area is length times width. Area is, what is the length of this rectangle? Well, it's not just x, is it? Well, if I have x and negative x, don't I get 0? Hey, if this side is 2, I know the coordinate of this side is -2, but, or sorry, not side, I should say. If this length is 2, and I know the coordinate of this length is -2, still, come on, how long is the whole thing? 4, right? And isn't that 2 times the positive x coordinate, because I don't want negative length? And then what is the width? What am I calling my width? I'm calling actually my height, right? The height. Well, what's the height of this one? And it doesn't matter which side of the rectangle I'm on because it's a parabola. Isn't the height 12 minus x squared? Length, width, or height. So my area is just 24x minus 2x cubed. Right? That's just a cubic with a negative leading coefficient. I know what that looks like, something like this, right? Maybe it has a max and min, maybe it doesn't, right? Or it looks like that, I don't know. 24x minus x cubed. So what do I, now I'm finally at the frickin' calculus. Now that I'm at the calculus, take the derivative. Now that I have an equation for area of what I want to maximize in terms of one variable x, now, what do the directions say? Do the first derivative test. So a prime is 24 minus 6x squared, a parabola that opens down. Set the derivative equal to 0. Since x is the positive, right, I'm using the positive coordinate. I don't need the negative. I am just going to use 2. Oh, no. I should have x at -2. That's silly. These are, remember, these are my candidates. And yes, I have endpoints, right? So I have x equals -√12, x equals -2, x equals 2, and x equals positive √12. Those are my candidates. I could make a number line and test, which I'm sure you could do. But in this case, I want to use the second derivative test, just to demonstrate another way. Use the second derivative test, the concavity, right, which is usually a concavity test, but for Extrema. Because the second derivative is easy to find, right? Isn't the second derivative is just -12x? So for the interior points, what is a double prime of -2? A double prime of -2 is positive, which tells me I am concave up. And remember, at -2 is where the first derivative was equal to 0. So the first derivative being equal to 0 and concave up is a minimum. But where a double prime at 2, right, -12 times 2 is negative, which means I am concave down. And because at 2 the first derivative was 0, I have a horizontal tangent, and at the same place I'm concave down, meaning that there is a maximum. So my endpoints, I think you can figure that you're not going to have at the endpoints, right? If you make a rectangle at the endpoints, these are minimums, because the first derivative is a parabola that opens down. So the first derivative is, right, so my first derivative, there's my first derivative, which looks like that. So certainly at negative root 12, my parabola is negative, so I'm decreasing. Sorry, wait. I want to make my conclusion here before I do my endpoints. I'll do the first derivative test over here. But I wanted to show you that with the second derivative test, I can show that at the interior point of 2, I have a maximum. If I were to do the first derivative, that's using the second derivative test. If I was to use the first derivative test, right, I would be plugging in a value like -1 over here. So -1 to my derivative is -6 times 1, which is -20, so I would have positive, and then negative, and then positive, right? Double check me on that, right? So if I'm at negative, whoops, I'm sorry, -1 is here, -1 is here after -2, and that's where I was positive. Below -2, like -3, so -3 squared is 9, -6 times 9 is -50 whatever, and 24, so I'm negative, right? So the interior point I got from the second derivative test, but also for the first derivative test certainly looks at that. When I look at my left endpoint, negative root 12 and root 12, remember using a left endpoint means I'm going to draw a, right, one side all the way here to here, right, but then my height is going to be 0, so that's, my endpoints aren't included. So I could use, I'm only looking at interior, so the first derivative test gave me 2, and the second derivative test gave me 2. So where, just showing you that you could use either test, and sometimes it's up to you to decide whether the second derivative test is a nicer test than first derivative, remembering though that the second derivative fails if the second derivative is also equal to 0. So did I answer the question? What is the largest area the rectangle can have? No. Did I answer that? No. What are its dimensions? Did I answer that? No. I found x is equal to 2. So where do I go to answer the question? The area function at 2, and the area function at 2. Then I have to, the length is 2 times the area, I'm sorry, 2 times x. And the width, or what I'm calling the height, is 12 minus 2 squared. So certainly the area is going to be and I'm not going to get full credit unless I put units. Now I have to say that AP probably would not care, since they're not actual units here, whether you put square units on it or not, or whether you just answered 32. Okay, so there's example 2. Example 3. Two sides of a triangle have length A and B, and the angle between them is theta. What value of theta will maximize triangle's area? So, I have a triangle with length A and B, and theta is between them. Now, that means A and B are not going to change. A and B are constants. That's important when I'm doing a derivative, right? Because from pre-cal, I know that the area of a triangle is 1/2 the product of the sides times the sine of the angle between them. Now remember, this is not going to take the product rule because that's all a constant. 1/2, so pretend A was 7 and B was 15, right? The area is 7 times 15 times 1/2, then times sine of theta. Theta is going to change, but not A and B. So the derivative of a constant times a function is just that constant times the derivative of the function, right? So I'm going to make a number line for A prime, and I'm going to look for places where A prime is equal to 0, and since I'm trying to maximize, I want to find where the derivative changes from positive to negative. So I set the derivative equal to 0. And I say to myself, when is 1/2 AB? Now that's not going to be 0 because A and B are sides of a triangle. So what is some number times cosine theta going to be 0? Well, that's when cosine theta is equal to 0. Well, when is that? When is cosine, using my unit circle, when is cosine equal to 0? Right? And pi over 2, and then multiples of that, but remember I'm talking about theta in an angle of a triangle, right? So that's not going to be more than, right, 180. So pi over 2. Now since my derivative is 1/2 AB cosine theta, before pi over 2, cosine is positive, right? Whoops, I wrote. Right? Think about cosine. The values of cosine in the first quadrant are positive, but after pi over 2 are negative. What does that mean about area? Area is increasing to decreasing. And I don't really care about an angle that is 0 or an angle that is 180 because then I don't have a triangle. So I'm thinking about endpoints, but not worried about endpoints. So what does this mean? What did I ask? What value of theta? So where do I plug pi over 2? Oh wait, pi over 2 is theta, right? So didn't I answer the question? When theta is pi over 2, or 90 degrees, the triangle's area. Will be maximized. Okay, so that's all for the first day. And then you have a homework assignment way back here. Right, a homework assignment in the book that you can spend some class time now doing or working through my class examples. Tomorrow you have the quiz, so that being Wednesday. No, Wednesday is class day, Thursday is the quiz, and then Friday we will go on with optimization problems, and I'll have another video ready for you where I go through these rest of the examples on this handout, so 4, 5, and 6, 7, and 8. And you will have class time on Friday to either watch those videos or to work on the book problems and work together on book problems so that your weekend is a little bit nicer. That's all for now. Bye.